Hey, hi everybody. Good afternoon. Thank you so much for joining us today. So as you know, in continuation with our Women Who Code Chennai chapter, we have a data structures and algorithm series that we have session 3 today. So Pavithra, thank you so much for taking time out and teaching us about trees. So a little bit about Pavithra. Pavithra is MTS3 at VMware, and she's the director at Women Who Code Chennai chapter. And she has given us too much knowledge about data structures and algorithms in the past two sessions also. I'll put the link of those videos in the chat window. You should go and look it up. And this is a continuation. And today we'll be talking about trees. So over to you, Pavithra, and thank you again so much for all of your time. And Pavithra, over to you. Thank you.
Hey, thanks, Shubhanji. So I hope I'm audible, right?
Oh, yes, you are audible.
Okay. So thank you all for joining the session. So we'll talk about trees today. So I think Shubhanji had already given a background. So it's going to be data structures, and the trees that we call in data structures is what we'll cover today. So I am planning it in a way that, we'll try to make it a little easier and try to consume the concepts alone, basically, how it works, what kind of implementation happens and all. So quickly, I'll just show the agenda. So it's going to be, what are trees, the main terminologies, because trees as a concept, it has a lot of terminologies revolving around it. So how do we represent it in our technicality? Like how do we show it? And what are the operations that you can generally perform on a tree? And how do we implement it? And a couple of real-time applications so that we'll try to get a flavor of why do we really need trees and where do we implement in real time. All right. So yeah, so I think these are the, like the core basics where in previous sessions we would have seen about arrays, we would have seen about linked list, stack, and all these are linear. So those were little linear where you store it like, one by one. A stack would be like one on the other, whereas tree is something which we call it as hierarchical. So because it has its own hierarchy. Okay. So now what could be the reason for a tree? So generally, main purpose would be like, search algorithms or easy searching and to ease out the search. That's the key purpose of it. And on top of it, I'm just categorizing it in this way. So binary tree, binary search tree, which most of us would have heard of. So binary tree, again, it has something called complete and perfect, all these. So this is just a high level. So we need not think too much now. I'll go to the actual concepts where we can talk in detail about it. So if you have any questions, you can probably put it on chat or you can probably stop me and unmute and ask your questions. So yeah, this is the actual slide which I've done to show all the concepts of tree. So we'll start one by one. So this is a tree, a typical tree structure. So all these, the circles, these are called nodes. So we call it as nodes. So it has so many nodes and it is widespread. A, B, C, D, E, F up to till P you have, and these are called nodes. Out of which the very first one is the root node. So we call it as a root node. And this one, the value that any node holds will be referred as key. So going forward, when we say key, it is going to be not the node, it's going to be the value it holds. It could be 1, it could be 2, 3, A, B, C, D, it could be anything. So the value, we would refer it as key. So, and then we'll move on to something called subtree. So subtree is nothing but, we know it's a part of the tree itself. And here you could see a parent. So as we know, so a root itself is a parent, just that it's a parent for the entire tree. When I say a subtree, it's going to be a parent for only its own child nodes. So that's why it is called a subtree, a tree within a tree. And it is a parent, and all these would be your child nodes. Among the child nodes, it's a usual terminology, right? Like we call sibling, brother, sister, that kind of relationship would be the sibling. These two would be its siblings because it's at the same level. So these are the key terminologies when it comes to node as a concept. So now something called edge. Edge, maybe if you'd have learned about graph algorithms and other things, you would have come across this. Edge is nothing but the line, the distance between two, let me not put it this way. I'll put it like the one that connects two nodes. That's what we call an edge. So A and C is connected with this one as its edge. So that's that's about edge. And now once we are little okay with all these, the top layer, the key concepts, what do we call each of it? We'll move on to this one. So all these ones are leaf nodes. So anything that is at the bottom, when I say bottom, it is just a depiction. So the one that doesn't have a child node, anything that doesn't have a child node will be a leaf node. All these are leaf nodes. And all the others, which are non-leaf nodes, we would refer it as something called internal nodes. And leaf nodes are also called as external nodes. Okay. So this is the basic structure of a tree. So now maybe you can let me know if you have any questions on it. Meanwhile, there is this just something to remember. So generally, we have seen the trees growing this way, the other way around. This was put intentionally just for our remembrance that in computer science, tree always grows downwards. It doesn't grow upwards, it grows downwards. So this is your root and followed by the leaves. So something you can remember easily. So that's one thing. And then we'll move on to a few other concepts now. So till now, if you have any questions, you can probably stop me and I'll be okay to take. And meanwhile, I'll just quickly recollect. Node, and this, the very first one is a root node. Value within is called key. And we have something called subtree, a tree within a tree. A parent, parents, child nodes, and the relationship between any of these, G and F, this one, K and L, M and N, O and P, all these are siblings. Okay, so this is the major concept. So now once this is done, we'll move on to something called levels. So we just have to remember few terminologies like level, degree, and height. So when I say height, height is the height of the tree, meaning the entire distance. So distance as in it is, you can probably take it this way. So height is nothing but the maximum number of edges that is required to reach your root. So from L, 1, 2, 3, and 4. So height of this tree is 4. Okay, so let me try with one more. 1, 2, 3, and 4. So from what is the maximum number of edges that you have to travel to reach your root node? So this is nothing but your height of your entire tree. So that's something called height. So this tree's height is 4. Okay. So now if I say what's the height of node B, then it's going to be 1, 2, and 3. So 3 is the height of node B. Node as in one specific node I'm talking about. Tree as in the complete tree. So your height would be with respect to the root. Okay. So that is about the height. Now coming to the other side, this side. Give me 1 second. Yeah. So this is something called levels. So levels, it usually starts the other way. So it starts from
Guys, you could please go on mute.
Yeah. So levels is something which starts from level 0 at root, and then it drops down to till the leaf node. So level is always like 0, 1, 2, 3, 4. So you can remember level like a tree. So from the top till the bottom, it drops down. So why do we have such concepts? It is because when we do it programmatically, like when we start applying it, writing a code for it, certain things will be easy for you to, have a loop. If you have to have a loop across the levels, then you will say how many ever levels it has, you will say for I equals 0, I till 4, something to iterate. So we just have to know the concepts. So maximum number of nodes at level L would be 2 power L. This is just a formula that we have to remember. So at any level, if you have to see how many nodes can be there, then you say 2 power L. Okay, so this is all kind of binary tree concepts. And then there is something called degree, which I said I'll tell you. So degree is number of children for a particular parent. So I'll randomly choose a parent. I'll choose C. C as a parent. And if I have to say what is the degree of C, I would say it's 2 because it has 2 child nodes. Okay. So now, what is the degree of P? If I say, P as such is a child node, is a leaf node. So degree of P is going to be 0. So degree can always be 0, 1, 2, only, any of these three numbers. So that you have to just have it in mind. Levels, it can keep growing as your tree grows, and it always grows downwards. Okay. So fine. So here I think we have seen about the entire structure, height, levels, and degree. So now the next slide is going to be something that we are going to do together. And I would just request you to probably put the answer on the chat. Okay. So it's not going to be something tricky and all. Whatever we spoke now, that's what is the question. So I have framed it in such a way that every concept will go through and immediately we'll see, we'll just test how far we are, we were able to crack it. Okay, you can.
One question, not sure if I missed it. What is depth?
No, depth I'm yet to come, Ashok. So probably I'll explain you in the other upcoming slide.
Sure, thanks.
All right. So yeah, probably maybe if I'll just give a couple of seconds. So this is a sample tree that I have it here. So what would be the number of nodes that it has? So maybe, you can either unmute and answer or. Okay, I can see Asha saying 6 number of nodes, 1, 2, 3, 4, 5, 6. Yeah, that's right, Asha. Yeah. Yes, that's right. Great. So I think we are good with that kind of questions, right? So now we'll proceed with root node. So what is the root node in this? Yes. All right. Perfect. So then I think I have to pace it up. Yeah. Thank you. What are the leaf nodes that we have? Leaf nodes DEF. Yeah. Perfect. Yeah. So how many levels? Number of levels we have in this? Okay. Okay, I'm getting combination of 2 and 3. Okay, we'll see. So number of edges that we have, how many edges we have in this whole tree? Okay, 1, 2, 3, 4. Okay, all right. What is the height of this tree? Height is 2. Okay. So Ankita, you get some. Okay, 2. Yeah, height of tree. Height of node A. So I'm not asking about height of tree. I'm asking about height of node A. Okay. Okay. All right. So I am getting combination of 2 and zeros. All right. So what is the degree of node C? Degree of node C would be? Okay. All right. Yeah. Fine. So I think we will see the answers and then probably a few things which I have got, more than one answer. Just we'll recollect the concepts with that answers. Okay. So I'll move to the next slide. Yeah. So I think all of us had, we are good with this. So number of nodes, it's 6. How did we achieve this? 1, 2, 3, 4, 5, 6, A, B, C, D, E, F. Okay. And what is the root node? Yes, A is the root node. It's quite evident. Leaf nodes, yeah, we are clear that anything that is there without children would be leaf node. So how many levels are there? So it is 3 levels. So 0, 1, 2, and 3. 3 levels. Number of edges is, yeah, I think this is pretty fine. Height is something which I got 0 and 2. So I just wanted to recheck. So height, I'll probably say height is something like you have to start from the leaf node, any of the leaf node, and try to go till the root. So you have to calculate what is the height of it. So 1 and 2. From here 1 and 2, and from here 1 and 2. So whichever is maximum, you'll take it. So in this case, it's going to be 2 because 2 is the maximum number that we got. And just imagine if this F node wasn't there, we would have said 1. C to A is 1, whereas E to A is 2 and D to A is also 2. So 1 and 2, the maximum is going to be 2. So that's how we calculate height. Height of node A is nothing but the height of the tree. So always we just have to remember that height of a tree is same as height of the root node. So root, we calculate with respect to child, right? So we always go up when we calculate. So that's why it's all 2. I think I got like 0 or something. So yeah, just have this in mind. We'll say height of tree and height of root node is always same. And degree of node C, yes, it's pretty straightforward. So would somebody like to try degree of node B? Maybe you can put it on chat. Degree of node B. All right, yeah. So what would be the degree of node A? Yes, that's right. All right, I think we're good with this. I'll move to the next one. Okay. So this is going to be tree versus binary tree and binary search tree. It's not a comparison, it is just for us to understand the concepts. So this is something the way that I understood when I read. So what we'll do is, we'll imagine a plain loaf of bread, and then a toasted bread, just a toasted bread. And we'll have something like on top of a toasted bread, we just have some sandwich, something within. Okay, so we'll just remember it this way. So the actual concept is like, you have some property. On top of it, you add another property to it to make it a toasted bread. On top of a toasted bread, you add some sandwich within, some stuffing within, and you make it a sandwich. Okay. So in that case, we'll see what is a tree, a plain tree. A plain tree is nothing but it's just going to have a hierarchical structure. That's the core thing. And it'll have node and children. There are no limitations, like no limits to number of child nodes that it should have. It can span across how many ever child nodes it needs. So 1, 2, 3, and it can even go to 4, 5, 6. How many ever it is there, it's perfectly fine. So that's a normal tree. We'll compare it with a plain bread. So now, what is a binary tree? So obviously, binary itself is a clue for us, right? Binary is going to be something like, we connect it with 2, right? So it's going to be 0, 1, 2. So we just have to remember that any tree, as in the tree property still remains the same. Any tree which has 0, 1, 2 child nodes, at most 2. When I say at most, that's a maximum that's allowed. So if it, a standalone node A, that can also be called as a binary tree, because it has no child nodes. It has only 0. It's a 0, 1. And here in this case, this has 1 and 2, 1 and 2, 1 and 2, and 1 and 2. So all the nodes have at most 2 child nodes. Then you can call it binary. This can even have 1. So we just have to remember, it can have 0 child nodes, 1 or 2. Then you can say it's a binary tree. Technically, it should not exceed 2. That's the logic here. It should not exceed 2. Anything less than 2, you call it a binary tree. Okay, so now we have achieved, the toast has been given. So on top of this toast, I'm going to add few more rules to it to make it a binary search tree. So whatever rules that we saw for binary tree, that's going to be applicable here also. Meaning it can have 0, 1, 2. That is still there and not more than 2. On top of it, we'll say, this is called left subtree. Anything that's on the left side of your root is your left subtree. Anything that's on the right side of your root is your right subtree. Left subtree should always have the lesser key. So, okay, I think key is a concept which we spoke in the very first slide. Can someone tell me what is the key of root node here? Based on what we spoke. That's right, Asha. Yeah. So F is the key for the root node. So with respect to F as the key, you have to compare all its all its left side keys. So A, B, C, D, and E. All these are lesser than F, obviously. And again, coming back to right subtree, I'm going to say G, H, and I, which is again greater than F. Okay, so till then we are good. We'll travel to B. B, A. So left subtree has A, which is less than B, and B, D, obviously greater than B. Again, from here, C is greater than D, and C is less than D, and E is greater than D. So the core idea is that every subtree, like everywhere you see two child nodes, right? Or one child node, how many ever it is there, your left subtree should always have lesser key, and right subtree should have greater key with respect to the node. With respect to the root. So the root or its parent, it can be either way. If you notice something here, G, right? G doesn't have its left child, but right child is there, which is I. So which is obviously greater than G. So that is okay. And H is something which is here, which is also okay. Just imagine if H has been put from here to this side, I mean from left to right, then it wouldn't be called as a binary search tree. So this is the core feature, as in core, what do you call the core rule that we have to think for the core property. We call it property for a binary search tree. All right, I think these are the things that we just have to remember. So any questions, probably you can put it on chat or unmute and ask me. The next slide is going to be a test as in the way we did, right? We'll quickly have a few trees and we'll try to find out what is what. Okay.
So guys, before we move on to the next slide, please ask your questions because you will be marked. You better get full marks. So ask your questions, clarify your doubts. So Pavithra, on that note, I had one doubt. So basically, like all binary search trees, like since we have given the example of bread, toast, and sandwich, so can we say that all binary trees are trees? And
That's right.
all binary search trees cannot be binary tree. I mean, it can be different also.
That's right. It goes this way. All the three, we can say all the three are trees only. End of the day, it's going to be grouped under trees. Whereas binary tree is a tree, but tree cannot be a binary tree. Similarly, binary search tree is a binary tree, but this binary tree can never be a binary search. So that's how it works.
Okay, got it. Sure.
Pavithra,
So-
Shankar.
Hey, Shankar, yeah.
So, Pavithra, this tree traversal, how it happens for the binary trees?
Yeah, we have
from
it in
root node, or it is from?
yeah. I get it. So we have it in the upcoming slide, Shankar. Maybe.
Okay.
Okay, sure. All right, I'll move to the next one. Okay, so there's something like who am I? So just look at the tree and check the keys and then try to guess what kind of tree is this. Okay, binary tree. Okay, binary. So can someone probably unmute, or maybe you can put it like, why don't it be called as binary search tree? Okay, Shankar says binary search tree. Yeah, right. Yeah, that's right, Asha. That's right. Yeah. Okay, so yes, so that's it's going to tell you that I'm a binary tree, and it's not a binary search tree because I have at most 2 children, but my left node is not less and right node is not greater. So I think Asha, yeah, that's right, Ashok. Yeah, this is how it is. All right. So we'll move on to the next one. Yeah, look at this and just we'll see what kind of tree is it. That's right, Asha. Yeah, non-binary tree. So why so? As in, like with which property we are concluding that it's a non-binary tree? Correct. That's right. All right. Perfect. Yeah, I think we're good. Yes, I'm a tree and not a binary tree because I have more than 2 children. That's right. Okay, I'll move on to the next one. Yeah, just look at it and BT. Okay. Okay. So why is it not a binary search tree and why is it a binary tree? That's right. Yeah. So when we say this, I think we also have to check the other nodes. This is quite obvious. So 7 and this itself will give you a conclusion that it's a binary tree. If at all you see 1 here, you just have to see the other keys also. Like, so binary search tree the property should be fulfilled across the tree for the complete tree. Okay. So yeah, but the answer is right. I'm a binary tree, not a binary search tree because the same property applies. All right. We have one more, I guess. Yeah. What kind of tree is that? Okay. All right. So I hope you have checked all the keys here, right? So 2, 3, 4, 2, 4, 8. So one question. So maybe anybody can feel free to answer, can ping. So if at all, if we say this is a binary search tree, and if I have to add a left child to it, what would be the key for it? Right. Yeah. It can either be 0 or 1 or anything in negative, like anything less than 2. That's right. All right. I think we are pretty good with this. So yeah, I'm a binary search tree because I have at most children, meaning I'm satisfying binary tree And also I satisfy the property that we all know which property it is. All right, so till this, I think we're good. Now we'll proceed to something more about binary trees. When I say more, it is kind of, with the binary tree in mind. So yeah, one call out here. Binary search tree as such is a very huge topic. So today we'll concentrate more on binary trees, and maybe in the next session we'll have splay trees and AVL trees covered. Okay. So we'll talk more about binary trees today. So with binary trees in mind, there's something called complete binary tree. So we'll see what concept is that. It is saying that, all the levels except the last level is completely full. So meaning you start filling, right? Your root, your left, your right, and you start filling one by one. So when you start filling this way, except the last level, all the other levels should be full. So when I say full, it means that, let's just give me 1 second. All right. So yeah, when I say it is completely full, it means that you just have to have all the nodes filled, like both left and right child should be there. So this would easily depict it, right? And one more main rule is lowest level nodes are filled from as left as possible. When I say as left as possible, it means you start here, you put 2, 3, 4, 5, and 6. And it should not be like you say 1 and you leave this left side completely blank and go to the right side. So these are the 2 properties we just have to remember when it comes to complete binary tree. Okay. So this one, the very first one, it is quite evident, complete binary tree. This is not complete. So why do we say it's not complete? Maybe any guesses? You can probably put it. Left side. Okay. Okay. I think Ashok, maybe one more try. Yeah. That is right, but there is one more property to it. That's right, Asha. Yeah. So 2 things. It is satisfying 2 things. One, which Ashok mentioned as the last one, he says it's not there, but actually it's the other way around. It should not be there. It is saying the last level, it's okay if the last level is not full. All the levels except the last level are completely full. So it is okay if we are not going to fill the last level. That's absolutely fine. But as Asha mentioned, 7 is incorrect. So it has to, if at all 7 would have been 3's left child node, then we can call it a complete binary tree. Why? Because last level is incomplete and you're filling from left to right. Okay, so here this is a missing value. So we cannot call it a complete binary tree. And why is this not a complete binary tree? I think that's quite evident. It's not following any of the properties, right? So either it is 1, 2, 3 is not there. So the second property is gone. 4 is there, but 5 is not there. Again, second property gone. First property still holds good, but both should be satisfied. Okay. So any questions to it? Because the first one is little confusing, as in it might be confusing because we are not saying that it should be full. We are saying that except that level, other things should be full. Okay. All right. Okay. So
Pavithra.
Mhm.
The last one, right? If the last node is having 3 means it will complete tree. The last one, 1, 2, 3.
This one, Shankar, not complete. This one you're saying.
Yeah. Yeah. Instead of 4, if it comes as 3, is it a complete binary tree?
Oh, no. So this is not a binary search tree, right? Where left and right and all. So even if 3 is there, if we have to read the first one, so all the levels except last level are completely full. No, second level itself is gone. This level is full. And you got it, right? And you have to start filling from left. 1,
left,
2.
Okay. 2 and
Here 3. So
right
if the
should
3
come.
that's right.
Should
If
come
3
here. Okay. Come here, then it would be complete. Okay. Got it.
Correct. I think this is a good question because we can think about it. So one question to you all. So if 3, if not for 4, and if I put 3 as a right child, what would we call it? Is it a complete binary tree? Can we say it a complete binary tree? No, that's right, Shubhanjali. Why? I mean, which property out of these 2 is it's violating? All right. Okay. So yeah. So if I have, so just imagine this part alone. 1, 2, 3. This part alone as a tree. It is still not a complete binary tree because the name says complete, but the rule says the last level should not be complete. It should be only the levels except the last level should be full. Okay. We just have to remember that alone because it is quite confusing. The name and the concept is confusing, but that's the rule here. So except the last level, all the other levels should be completely full. Last level should not be full. Last level should have an empty space, and that empty should be, it should start from left to right. Okay. Maybe should we give it a try because we have few questions around it. Can somebody put
One more question. So if in the first picture, if in the 3 node, under 3, if we had another one, say a child coming out, say 7, so it would not be a complete binary tree.
That's right. That's what I was trying to say. If we would have had 7 here, then we should not call it a complete binary tree because though it is satisfying the second one, the first one is gone. Except the last level, all the other levels should be full. Last level should not be full. Okay. So we just have to remember that way. So I think it's fine. We'll see a few examples and then probably we'll try to see how it is. So now the second one is perfect binary tree.
Hey, Pavithra, I have one question. Can you go to the previous slide? So on the second tree, see, what I was trying to say is like, say, since the left node on 3, since the left node is not filled up, and then without doing it, we have come to the right node as in like,
Correct. That's right. That's right. Yeah. In that, yeah. In that.
So what if I have this 7 on the left instead of putting it on the right? Then it means it's a complete binary tree, right?
Correct. That's right. It would have become this way. It would have been a complete binary. That's correct. That's right. Yeah.
Okay.
Pavithra, I have one question. So in the last third one, so in case we have 3 on the right hand side.
Right of 1 or right of
1? Right of 1.
Okay.
And then to the left of 3, we have something like 7. Okay, so is it a complete binary tree?
No. So 1, 2, 3.
Okay.
Till this we are good. The moment you
Yes.
go to 4, you need something here called 5 or something, and then only 3. You said it should come.
Oh, okay. So 2 also has to be filled.
Correct. So you start filling from left to right. You start filling up one by one without any gaps, and it should be incomplete. The last level should be incomplete. So
and I think one thing to add up here. So suppose if I have 3 onto the right, and that's it, and it still is a binary tree, right?
if
I'm not. Yeah, I add a 3 onto the right, and we are done, right? So it's still a binary tree, no?
Correct. A complete binary tree. It's still a
complete binary tree.
Correct.
And say if I have 3 on the right and 2 I'm extending and saying I'm putting a 5.
Correct.
It's still a complete binary tree.
Correct. That's how you fill it, as in 1.
So you just have to make sure that left and right is, you have to come from left to right, 1.
Correct.
And left has to be completed, and then you have to come to the right.
Right. That's right. Yeah. That's correct. All right. So yes, we'll move to perfect binary tree. So perfect binary tree, it says something like, okay. So I think Ashok, I'll come to your question now. So depth is, you can compare it with, depth is something which we can talk separately because we have already seen height, level, and degree. So we're not confused with that. But depth, more or less, it is same as edge calculation, your height calculation. How deep you go. Height is something like how you reach the root from the leaf. Depth is something like how deep you can go. Okay, so in this case, all the leaf nodes are at the same depth. When I say all the leaf nodes are at the same depth, so technically what does it mean? It means that all the leaf nodes should be filled. Okay, it's a perfect binary tree. And lowest level nodes are filled from left as left as possible. Okay, so technically, when you say the first rule is correct, then the second rule will obviously happen for you. So whatever we had a little bit of confusion with the word complete, that you can fit in for perfect, which means there is a perfect person than a complete person. So perfect is this one because it is complete, fully complete. Okay, we'll just forget about others. We'll just have this one as the example. And this is obvious, it's not perfect. Okay.
So a perfect binary tree can be called as a complete binary tree, and the other way around is not right.
No. So this one, we categorize it as in, at least to what I've read through, we categorize it as two separate things. It's not like a subsect of it, it's a type of it. Okay. Okay, we'll just give it a try, but this little, we have ABC, a lot of it. But I'll go one by one, and then you can probably, ping the answers with putting A and then what is it? Okay, we'll start with A. So now I'll probably give you options. The options is something, whatever we have read so far. It could be binary tree, binary search tree, complete binary tree, perfect binary tree. So 4 things. Just remember that, and we'll go one by one. So what would be the first one? Okay, A. Okay, I also said you have to think about complete binary tree, perfect binary tree. So at the basic level, binary tree is correct. And then does it fall under either any of it? Correct. That's right. So yes. So the first one is complete binary tree. Pretty straightforward, right? So we started from here. The last level, that is the leaf node, is still incomplete, which is correct. And we started filling from left side. That's correct. So now we'll move to B. What about B? Okay. Okay. Yes. All right. Okay. All right. I think I got it. So I'll explain it again so that I think, Asha, you got it right. So this is a binary search tree. So why do we call a binary search tree? We'll recollect one by one. Binary tree, yeah, this is also a binary tree, right? All these trees we can still call as a binary tree because everything has, 2 children, at most 2 children. So the entire, whatever we see, it's a binary tree. And we have to just check, is it a binary search tree or a complete or perfect or just a binary tree? On that node, as Asha mentioned, this is a binary search tree. Okay. It has this key value, like, 2 is this side, the right subtree, the value is higher than the root. So this comes under binary search tree. Yeah. Ashok, I think Ashok and Ankita, it is still a binary tree. So your answer is also correct, but it's partially correct. Like we have one more flavor to it that we just have to look at this way. The first one, we cannot call it as a binary search tree, right? Because it's violating the property. This is a binary search tree. So yeah, moving to C. So, yeah. So when we say binary search tree, we have to ensure that even the subtrees are not violating the property. The entire tree should hold it. Correct. All right. Okay. Fine. I think Asha, you got it right. So this is a binary tree. So why do we call it as a binary, just a binary tree? First, we'll talk about why is it not a binary search tree. Anybody, maybe Asha, you can think, why is it not a binary search tree?
Yeah, because 2 is on the left-hand side.
Yeah, that's right. Shubhanjali, you're right. Yeah, that's right, Asha. So now we'll go to why is it not a complete binary tree?
It's not filled on the
Correct.
left.
It's not filled. It's not filled. Without filling 3 here, we have moved on to the next level, so which is not a complete binary. Obviously, there is no question about perfect. We'll leave it as is. Moving on to D. D. Would anybody like to try? Okay. Okay. Yes, that's right. It's a binary tree. So it's pretty straightforward, right? Because it's not a binary search tree because of obvious reasons. 1 and 2 is violating. 2 and 3 is again violating. Sorry, 1 and 2 is okay, but 2 and 3 is violating. And also it is not a complete binary tree because this one is not filled. All right, so it's a binary tree. Now moving to E. So E is, okay, binary search tree. So binary search tree, we have a property, just to recollect. We have a property that left should be always less than the root and right should be greater. Right. That's right. Yeah. I think I think I can. That's right. Shubhanjali and Asha. Correct, Ankita. So yes, first of all, we know it's a binary tree. Second, not a binary search tree. Evident. Third, is it a complete binary tree? No. Why is it not a complete binary tree? Anybody would like to take it? Because I think it's obvious, right? It is filled. The leaf is filled, so it's not a complete binary tree. And yes, the answer is perfect binary tree. All right, we'll move to F. So just look at, we'll go. So this is a binary tree we know. Okay, Asha. That's right. That's right. Asha and Ashok, you're right. So Ankita, it's not a perfect binary because it's not completely filled, right? So it cannot be a perfect binary. And yes, Ashok and Asha, you are right. It is a complete binary tree because it's not a binary search tree for obvious reasons. And it's not a perfect binary tree because it's not filled. And complete binary tree, it's correct. 1, 2, 3. So till the levels that is above the leaf level, we are good. Moving to the leaf node, yes, it is incomplete. And also we have started from left to right. So it's correct. That's right. Yeah. So the final one, G. That's right. Yeah. Asha and Shubhanjali, that's right. So it's a perfect binary tree. So it has everything there, all the properties are solved. And obviously it is violating the other whatever we spoke about, the binary search properties and complete binary tree. All
So
right. I think
complete binary tree is never actually complete, right? So there always there should be some things.
correct. So that's why complete, when we think about complete, we feel it's complete, but we have to always think that there is somebody even more perfect than complete. So perfect is the topmost complete we can, the
Okay.
English form of complete that we think about.
Okay.
Fine. Yeah, I think whatever we discussed, it's all here. So we are good. Okay, so now we'll go to, I think we have 10 more minutes, so I'll try to complete it. So there's something called representation of a binary tree. So while you code it, right, like how do we represent it? We have seen the node, key, left, right. So this is just a simple Java class. So you define a class node and you say something called key. Why do we need a key? Key is the actual player here. That's your value. And node is a pointer. Pointer as in it's going to hold your left and right, pointer to your left and your right. So it's kind of address type of thing. The one where you go, you access, and left will have its own key, right will have its own key. Okay, and public node, this is just a sample code. Maybe you can just think. Key is the item that you pass, you assign it. Left and right, initially it would be null for a simple tree. Okay. So we can talk more about all these technical aspects when we talk about binary search tree. It would be even more clear because we have search, sort, and other things would be there. So now coming to operations, typical operations. You can insert, remove, search, delete. And yeah, I think as Shankar, you asked for traversing, right? We are going to go into that only now. So there is something called traversing. So insert, as the name says, you insert. How do you insert and all? We'll talk about it. Remove, you remove one of it, remove a node. Okay. Search for an element, delete, and traverse. So technically, to do any of the initial 4 operations, the key operation that we have to know is traversing. If you have to insert, we have to know how to travel through this tree and find the correct position for it and insert your value there. For that, you have to know how to traverse. Again, remove, you have to search the entire tree. So search comes there. You have to know how to search. For searching, you travel again. So traversing is one key part of binary tree because you have to go deep into the tree and find your position. Yes, so this is what it is. So tree traversals, generally, it is categorized based on the algorithms, like, depth first and breadth first. Depth, it's the same, the English meaning of it. Depth is something like, this side we call it depth, and this is your breadth. So when I say depth first algorithm, it is something that you're going to go deeper and deeper from the root. You keep traveling from the root and you go deeper. And breadth is something you go across, cut across this side. Okay, you go level by level. So breadth is more towards level, depth is more towards your left, right, and it's something of that sort. Okay, so under depth first, you have three types of traversals. That is pre-order, in-order, and post-order. So I think the name itself will give you a clue. So pre-order is something like your current node, your left node, and then your right node. Okay, say, let's not have this bigger diagram. We'll start with this subtree, like 11, 7, and 12. Imagine this is your tree. Then what would be your pre-order traversal? Your pre-order traversal would be current node. Okay, 11, 7, 12. When I say current node, you can take it as a parent. So the current node is the node which you're traveling, you're in now. So 11, 7, 12, 9, 15, 8, this way. Okay, node, left, right. In-order traversal is something like left, node, and right. So left, node, and right. You're going with the triangle. So left, node, and right. Post-order traversal is the final option, obviously, right? Okay, give me 1 second. I think I'll just have to check right, left node, or it's left, right node. So mainly all these are positioned based on your current node. Your current node will be first, your current node will be in the middle, your current node will be at the end. This alone, I'll just validate. Okay. So these are the three types of traversals that is possible. And when we come to breadth first traversal, breadth first search, it is quite straightforward, level by level. 10, 11, 9. Then 7, 12, 15, and 8. Left to right, level by level. Okay, so we have a small exercise towards it. So I think this is a typo. So just sorry for that. So it's going to be left, right, and current node. Okay, so left, right, and current node, left, right, and left. The three options: pre, in, post. Okay, so we'll do one exercise on this in the next one. I think the answer is already given, so it's not an exercise, just for us to understand. So yes, so this is your tree, depth first and breadth first. So in order, if I say that we have to go in order, then how do we do? Left, visit the root, right. So all these something we spoke in the last slide. Now I'll come to this major part. How did we achieve with this? So what you have to do is, this is your current node. Okay. And for in order, it's going to be left first. So left. You take left. Now you have to check if left is the leaf node or not. If left is not a leaf node, you have to go deeper in order itself. How do you go deeper? Left of left. So you start from 4. 4, 2, 5. Okay. 4, 2, 5. Within the subtree, you're done with the in order. Now, across the tree, you're going to do. Now, entire left, visit the root, and right. Okay. So 4, 2, 5. And then you go to 1. Your root, and now come to your right subtree. That is the third point. In the right subtree, what you have to do, you have to again do one in order. How do you do one in order? 6, 3, 7. Okay. So this is how it keeps on recursive. So we call something called recursive algorithm. So you have a loop and you keep going to left of left, and in order, it would be like you travel to the leftmost child. You start with the root and you say left of left, and then it keeps on going. So you'll finally find a place where your left is null. Null as in you have reached the child node, like the end of it. From there, you'll start your traversal, left, root, right. This entire left, root, right. Within the right, left, root, and right. All right. So this is about in order. So we'll do pre-order, which is again, visit the root, left and right. So start with the root. So that is straightforward. Visit the root, left and right. So 1 is done. How did we achieve 2, 4, 5? Within the left subtree, you have pre-order. 2, 4, 5. Okay. Visit the root, left and right. 2, 4, 5. Again, now we are here, right subtree. We are going to the right subtree. Within the right subtree, you're going to follow this same. Visit the root, left and right. Visit 3, left, right. Okay. So 1, 2, 4, 5, 3, 6, 7. 1. This entire set, 2, 4, 5. This entire set, 3, 6, 7. So this is what we call a pre-order. So pre-in as in, it's in the same order. Pre as in, your root comes first. It's pre. Post, your root comes last. Okay, left and right doesn't change. My bad, I have to change the slide. It's a typo. So left and right doesn't change. Just have it in that sense. So post order, I think by now we should be a little comfortable with post order. What do? You go to the current node. From here, what we do? Left, right. So first start with left. Within left, right, and root. 4, 5, and 2. Okay, done. Now after that, where do you go? Right. You completely leave this root and you go this side. Within this side, how do we go? Left, right, and root. 6, 7, 3. Now we got 6, 7, 3, we got 4, 5, 2. This order. Finally, visit the root. 1. Okay. So this is how we do this depth first search, where we go deep into the tree. Okay. And now breadth first is something which is like level order, left and right. There is nothing, to it, just left and right. So you start with root 1. You go level by level. So level, first level, second level, third level. 1, 2, 3, 4, 5, 6, 7. Okay. So just a point here. So if at all we would have followed a binary search tree here, if this is not a binary search tree, it's just a binary tree. If we would have followed a binary search tree, how it would have been? It would have been like 1 would be here, 2 and 3, 4, 5, 6, 5, and 7. So with that binary search tree in place, if you would have done in order, you will get it in sorted order, in your ascending order. Okay. So that is one thing that generally, for binary search tree, they'll do. So any questions on this traversal, at least binary tree traversal?
I have one question, Pavithra. So how do I decide, suppose say if I'm talking about depth first search, say, and if I have a requirement to delete one of the nodes somewhere in between, maybe say 3, for example, in this 3, say I want to delete 3. So at this point in time, how do I decide which search I should take and which would be optimistic?
I get it. So probably I'll try to understand. I'll try to explain you based on my understanding. So generally, these are the concepts that is already put in place. But when it comes to reality, based on the real-time application which we are using. So for example, trees are typically used. We have it in the upcoming slide. Trees are generally used in your folder structure. So we have a folder within a folder, and finally a file. So file is something like where it cannot even break further. So that's your leaf node. So in this case, internally, I'm imagining like the operating system would have had an algorithm to, the moment we search on our computer, right, for any random file, it would go do one of the tree traversals and it will find. So now when you ask me, how do we choose among all these? I think it would vary based on our scenario. So if it is a binary search, if you know it's already sorted in ascending order, you blindly go for in order. So you directly travel to your left. And one good thing about binary search tree is, you know that this, once you come here, anything that's to your left will be lesser. So if you have to find an element, say 2, I obviously know that if 3 is here, I have to go this side only. I cannot go this side. So based on that application and its requirement, I think they'll choose on, how it varies and what kind of traversals they'll opt for. Okay.
Yeah, thanks.
Yeah. All right. So this is the same slide. I'm going to revisit now. So now we understood how we would typically travel through a tree. With this in mind, I think we can imagine about how do we insert, how do we remove, search, and delete. So first you travel, search an element. And the moment you search an element, you can remove it, meaning the element that you have to do. So remove and delete are a little different, but I'm not going to cover it at this point in time because of time constraints. We will talk about all these as a part of binary search tree because the core concept remains the same. Just that the operations and all the other things also is the same, except for the property that we spoke about. Okay, we can talk in a technical term, like, we can have some coding and then we can implement and see how do we search, how do we remove and all right. So I think I'll quickly, we have one more minute. So yes, this is just a implementation using array. So imagine how can we implement a tree with an array when you have to represent it as an array? A hierarchical data structure, if you have to put it in a linear form, then you can probably fill it this way, right? 0, 1, 2, 3, 4, you have array and you say 1, 2, 3. So when I say 1, 2, 3, can someone ping on the chat what kind of traversal I have done? Maybe should I go back to the slide? So just see 1, 2, 3. So is it a breadth first or depth first? That's right. Yeah, breadth first. Yeah, BFS. So breadth first search is what I've done, and it's 1, 2, 3. That's how it is. Yeah, that's right. All right. So yes, real-time applications, if you see, it is something like DOM structure in HTML. So we all know web pages, right? So web pages, before that, real-time applications of tree, a plain tree, which doesn't have any constraints, which doesn't have any, the child node, number of child nodes and all. Here, the implementation is DOM structure in HTML, where you have your HTML head, title, body. It keeps growing, right? So this is something which is internally handled with, which could be handled with a tree. Okay, then coming back to File Explorer, as I told in the previous example, right? You have multiple folder within a folder, and finally you see a file. So file is your leaf node, and you have multiple folders to it, and this can maybe match with your tree structure. Okay, so these are the two real-time applications, and next slide is about other applications. Yeah, sorting algorithms. So in sorting algorithms, we'll be using binary search tree. So because that's the one which is going to give you this ABCD. You have D, all these things, it'll give you ABCD. How does it give? Because of the property. With that property, with your traversal, you can probably achieve that. You can achieve your sort and search. And decision trees. This is one key application for your binary tree. Previously, we saw about trees in general for folder structure. This is binary tree. Binary tree, I think you always have yes or no. There is nothing like maybe in that case. So you keep asking questions. So, imagine the small flash games that we would have played in our school times, which is going to click on a click of a button, you say yes, no. Based on yes, it will ask you next question. Based on no, it will take you a different direction. So here it's like, is it big? No. Does it live in a cage? This side is no. So no. Does it meow? If it's a meow, then it's a cat. If it's above, it's a dog, right? So it's not a meow. So it's a dog. So a typical decision tree can be easily handled with binary tree structure. All right. This is AI, like our artificial intelligence games. Most of it uses binary trees because of its decision-making capability. All this, you can literally divide based on the player's move. You can give them a completely different direction. So you don't have to come the other side. You don't have to go to the left direction. You can go to the right. Again, based on this question, you can go to this side and it keeps on going. Okay, so these are the applications. Yes, I think I'm already on top of the heart. So I think I'm pretty much done. Any questions so far?
No, Pavi.
Okay, all right. So I had this one to discuss, but yeah, I think we are already on top of the heart. We'll probably continue in the next session. When we talk about binary search tree, I'll probably, I just wanted to show a code and, the Java implementation of a sample problem. So for a given tree, like how do you travel and how do you compute a height technically? Okay, so I had it in mind, but yes, we'll discuss in the upcoming sessions. All right.
So thank you so much, Pavithra. So Cynthia, we will be uploading the recording of this session on our YouTube. And regarding the slides, yes, I think Pavithra, that's for you. Like, will we be able to share the slides, the deck?
Sure. Yeah, probably, Shubhanjali, we can discuss about it and we can share it with the meetup members on an email or something.
Sure. We will be sending you an email, and in any which case, the recording will be uploaded on YouTube, for which the link I had put in the chat. The entire DSA series is available. Please go and make use of that. Okay, so I think this was a wonderful, wonderful session. Okay, so there are a few questions, Pavithra. One is, do you have the Java program for the current and previous sessions? Sendil was
Yes.
asking.
So I think, Sandil, in this session, we didn't cover any programs. We'll cover it in the upcoming session. In the previous session, I think for Stack, we just had a couple of programs. We have a YouTube recording for that. Probably we can share that with you through our Meetup channel.
Yeah, let
So-
me also put the link here. I will put the link of the entire DSA series for you to go through, and you can go through that. And you can also actually give us your suggestions on any topics or anything that you would like Pavithra to cover in the DSA series. We would be glad to take that up also.
Yes, yes. Sindhil will probably keep you posted on that. Okay, once we are ready, we'll share the thing. Maybe you can follow our meetup page, so that would give you the updates on it. Okay. Sure, Cynthia. Yeah, sure. We'll do that.
Yeah, so that is great. I think, yeah, we will definitely be doing it very soon. Pavithra will again come back with very good questions. And I mean, thank you everybody for such an interactive session. And thank you, Pavithra, for making it so clear. Now I can differentiate about the different trees and all. So that was great. Thank you for making us doing that exercises.
Thank you.
And
Yeah, I think maybe Shubhanjali and I, we would request you all to, share this meetup page with your friends. And yeah, I think it's going to be more of collaborative session, and we can learn mutually. So that's the intent of this session. So it's not like, even I don't know the complete data structure, like nobody can do that. But yes, anything that you would like to discuss here, and anything if you would have, probably I think we can use it as a study jam where we can share. Okay, so I'm just trying to convey what I learned, and even I'm waiting to apply and do it in real time. So yes, feel free to reach out to us anytime. You can mail us on Chennai at womenwhocode.com. So Shubhanjali and I would respond to your queries. Okay.
yeah,
So thank you.
also I'm just Yeah, I'm also just curious if you could put in the topics that you would want to hear next so that we can plan the sessions accordingly. Just put 1-2 topics that come on top of your mind regarding data structures. Email. Okay, yeah. So I'll put the email here. And yeah, in the meantime, I think we'll be in touch. We will definitely be sending out the recording link to you all. And let me put the email for you all quickly.
I think I'll just share it, Shubhanjali. So it's our women code name.
Okay, perfect. Yeah. So yeah, we are looking forward to a lot more of your suggestions and looking forward to seeing you all in our upcoming sessions. So this DSA series will continue and we will come back very quickly and very with a more informative next session. And thank you so much for being a wonderful audience. And Pavithra, that was amazing. This hands-on part was very good. Like I could totally see how I am answering so many questions wrong. That really helped go back to the basics and learn again. So thank you.
Thanks a lot, guys. Thank you. Have
Thanks,
a good day.
Pavithra. Thanks all.
Thank you, everybody. Yeah. Bye. Have a good day. Have a good night. Bye.
Bye.